Welcome to another video covering the riscure embedded hardware CTF. Basically, it's about hacking an embedded device as part of a competition, and if you want more details about it, check out the introduction video and the playlist. Also, at the time of releasing this video, the competition is over and the sources should be available and you can set up your own Arduino Nano board to follow along. You find some links in the description. But now let's check out the challenge. So now that we have solved the first two easy challenges, and Jumpy was already pretty hard for me, I decided to write a little program that crawls the current scoreboard and counts which challenges have the most solves. This way I can see which challenges I should be capable of solving. And it looks like the photo manager will be our next target. It's another exploitation challenge. The story here doesn't tell us any technical information, so let's head right into it. Download the hex file, flash it onto the board and start a screen session to interact with it. So, the first time I approached this challenge, I didn't really follow a structured path and basically just played around with it. I found the bug quickly, but then I tried to actually solve it with the bug I found and I didn't have a good mental picture on how to move forward. Basically all my information was jumbled up. It's difficult to explain what I mean because my solving attempt itself was so messy that it's not possible to explain my thought process, because there was none. Sometimes that approach is okay because it can be very quick if you get lucky or know what to do, but here I failed. I wasted actually like 2 to 3 hours on that until I decided scrap all that, start over again, which was the right decision. I kept turning in a circle. For the second attempt, I didn't try to rush the solution but properly structure the attack. Basically, we follow the scientific method. First, we observe behavior, then build a mental model of the system on which we can create certain assumptions that we can try to prove or get them disproven and adjust the mental image. This means we go step by step. First, what can we actually do? We see a menu with two options, login and memory manager. With the login, we can apparently enter some tokens of the length 8 that contain these letters. If we do that, we get a welcome message and those 8 characters back. There's also a memory manager option that displays the total memory space and the currently used space. So, in our mental model, we can take note that the login name seems to be our only input we have. So, whatever our attack will be, it's very likely that it will at least start with some login input. The memory management seems odd for now, but probably might be important information. Why else would it be there? We can also enter some more characters, this time less than 8, and notice that the previous A's are still there and were simply overwritten. Interesting, maybe useful, maybe not. It also didn't change our memory usage. We can also try what happens when we enter more than 8 characters. In this case I tested 16, it did overwrite the A's, but still only 8 characters are printed. And again, memory usage is not affected by this. Okay, so we can assume some kind of fixed global buffer for the input because we always overwrite and work on the previous entered data. So if this is some limited memory space, let's see what happens when you enter a lot of data. I keep the letter A pressed to send a lot of it and suddenly we get a stack cookie corrupted message. Awesome, so the buffer we operate on seems to be on the stack and has a cookie at the end. A stack cookie is a simple buffer overflow mitigation, which means you place a random value after your data, which is checked before, for example, the current function returns. And if the value is still the same, the cookie was not overwritten, right? So no buffer overflow took place. But in this case, the application doesn't quit or reset, and thus maybe not regenerate the cookie. This means we can slowly brute force the correct value. Even if the cookie were always random, it might only be 1 or 2 bytes long, which we can simply guess correct by chance because we can automate it and let it run for a while. So to explore the stack cookie further, we first need to know how long the input has to be to override it. Let's write a script. We can copy some code we have written before to interact with the board. Because we still don't know what the memory usage is for, we better not ignore it completely, but keep that information with us. So we select menu option 2 and read that data. Then we select option 1 to log in and simulate the keeping a key pressed by always only sending 1 character. After each character we check if the board sent us the corrupted cookie alert, and if that is the case we leave the loop. Otherwise we increment the counter, which counts how many characters we have sent. at the end we can print the used memory and the length we need to overwrite the cookie. When we now run it, and you paid attention, you might notice that the used memory number changed. Actually, it changes every time when we make a new connection with the board, and not only that, now we see that the length that is required to hit the stack cookie also varies. Doing some simple math reveals that the memory usage and the length required for the overflow is correlated. This means by knowing the used memory, we can calculate now how long the input has to be to overflow the cookie. Cool, so let's write a loop that brute forces the cookie value. We don't know yet how many bytes the cookie will be, so let's start by brute forcing the first byte and then go from there. Basically, we loop over every possible byte value, then wait for the menu to be written, select option 1 to log in, send enough A's to fill the buffer, plus the character that will overwrite the cookie. Actually, I had that calculation here wrong because I never found the correct value. I sent 1 A too much. Anyhow, once we would find the character that did return a corrupt message, we can stop the loop and use that to explore the next byte. Also, the loop should not start at 0 and also not include new line or carriage return, which is hex A and D, because they probably end our input prematurely and we don't want that. So once we find a valid cookie, we can then basically use the same loop again and brute force the next byte after the cookie. Obviously, we don't know yet what the next byte means. Maybe the stack cookie is 2 bytes long, or maybe something else. So let's remove the break here and let us see the responses for all possible bytes. When we run this now, we will find the valid cookie quickly and then go on to overwrite the byte afterwards. And that byte seems to control the length of the input. See how overwriting it with 1 only outputs 1A, or overwriting it with 8 will have 8 A's? And you see that after 8 it will start complain to say that the input is now too long and it is exactly the byte value again. So this byte controls the length. Interesting. No idea yet what that could be used for, but we can update our mental model on how the memory layout looks like. Maybe we have to explore a couple of more bytes and find something that could be used for an attack. What? The flag? Our loop finished and it looks like the highest value for that byte, hex FF or 255 in decimal, triggered the flag output. That was unexpected, but I take it. This challenge was really a good reminder for myself that I should not approach a challenge without a plan, but follow a structure, make notes and really think about what I'm doing. Once I did that, it was really straightforward. There was not even ambiguity in our mental model. Each step was a logical progression from the one before. That's like a very simple Sudoku where you don't have to pre-calculate multiple steps in your head in order to figure out if a value is correct or not. Just keep going forward step by step.